So conservation of energy, as long as there's no, energy loss to friction or heat, what we have is on our equation sheet, we have the conservation of energy equation, which is written as KEI plus PEI equals KE final plus PE final. And so what that means is all the initial energy should equal all the final energy added up. So if we add up all the energy before, they should equal all the energy added up. It can be, changed. So kinetic energy initial, we just look on our equation sheet, 1/2 mv initial squared plus mgh initial equals, and then final, 1/2 mv final squared plus mgh final. And yeah, we can look at the energy transfer here, and that can be very useful for us. So let's start with this one here. At 1.23 kilogram tennis balls hit straight into the air at a speed of 13 meters per second. What is the kinetic energy of the ball? And then using conservation of energy, determine how high the ball will rise into the air relative to its starting point. So yeah, I'll go ahead and pause the clip, and let's see if you can figure this one out. And when you're ready to check, you can hit play to continue. All right, so we've got our kinetic energy starting out 103.935 joules. And using conservation of energy, we would figure out how high it goes. So we have conservation of energy, and the initial height is 0, right? It says relative to where the starting point, so we'll say 0 meters is starting point. And then what's the final velocity at the top? 0 at the top. All that potential is going to turn into kinetic. And so now we can simplify that. Remember, we can cancel mass from both sides, and that can be very helpful. Now, in this case, we did have mass, but you don't have to necessarily. So you can cancel mass from both sides, and we'll solve for how high it should go. It should go 8.622 meters into the air. All right, so for this one, a ball is thrown down with 2 meters per second speed off a 14-meter tall building. Using conservation of energy, find the velocity it will hit the ground with it from that height. And so, yeah, I'll go ahead and pause the clip, write out what each variable is, and then when you're ready to check, you can hit play to continue. Okay, so conservation of energy, the final height is 0. We can cancel mass from both sides, and because every single term has mass, and we can solve for, we know the initial speed is 2, we know the initial height was 14, and we're looking for the final velocity, really speed there, we have to assign the direction, and we should get 16.685, and if we have velocity, we have to distinguish the direction, and so that would be downward or negative, so you could have either there. So power is the rate at which work is done. So we take the work done in joules or meters, and we divide it by time, and that will give us the power output. So let's go ahead and try that with this one here. H24 16 kilogram box is being lifted in the air over a distance of 1.5 meters. If it takes 8 seconds, how much power is exerted in raising the box? So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so lifted 2 meters into the air again. If it doesn't say it, you can assume that it's lifted at a constant velocity. So the sum of the force in the y, positive force applied plus the negative force of gravity. Acceleration is 0, so the force of gravity is equal to the weight. Force applied going up, so 156.8 newtons. And we can get the work, so we know the force, we know the displacement. The force is up and the displacement is up, so cosine is 0. And we get our work, and for power, we divide by 8 seconds, our work, and 29.4 watts is the power output. Another thing that we can do here is look at how net work will change the kinetic energy of the system. So we have to find net force, and once we find net force, we can calculate the change in kinetic energy. So let's go ahead and try this one here. We have a hockey puck that's being forced to the right here, we'll say 0.27 kilogram hockey puck with a force of 39 newtons over 18 centimeters. And we want to find the final velocity of the hockey puck as it leaves the stick. So yeah, go ahead and pause the clip and find the final velocity here as a result of this. And when you're ready to check, you can hit play to continue. Okay, so we've got our force applied, and that's our net force. In this case, there's no friction. Work net equals a change in kinetic energy. We have our force. Displacement is 0.18 meters, 18 centimeters. And the net force is to the right, and the displacement is to the right, cosine of 0. The initial velocity is 0, and we're looking for the final velocity. We should get 7.21 meters per second as the final velocity leaving the stick. All right, now on this one, we have some friction holding us back. This is a ball being kicked with 27 newtons of force, and the force is, we'll say the force applied to the right, force of friction is back, and the ball is the foot is in contact with the ball for 15 centimeters. And again, starting from rest here. So yeah, go ahead and pause the clip and give this one a try. You're gonna have to find net force first, and then you can get the net work. But yeah, go ahead and pause the clip, give this a try, and when you're ready to check, you can hit play to continue. Okay. So positive force applied plus the negative force of friction. And in this case here, positive 27 plus negative 2, so 25 is the net force. And therefore, for work net, we use 25 newtons. 15 centimeters is 0.15 meters, and the net force is to the right, positive. And the displacement is to the right, and so cosine of 0. We have our mass, and the initial velocity is 0. So we're looking for the final velocity. So it should go off of off her foot at 3.10 meters per second.